The diagram shows two bumper cars, P and Q, at an amusement park. Q was stationary. P was moving at a speed of 2.1 meters per second towards Q. P collided with Q. After the collision, they moved off in the same direction. P moved with a speed of 1.15. Q with a speed of 1.57. Show that the total mass of Q was about 150 kilograms. Total mass of P is 250. Okay, so clearly this is a momentum question. So momentum is mass times velocity. And we also know that momentum before the collision is equal to the momentum after the collision. And this is the sort of process you're going to have to go through any sort of collision question. So what is the total momentum before the collision? Well, P had a momentum of its mass, which is 250, multiplied by its velocity, which was 2.1, and Q had a momentum of its mass, which is 150, multiplied by its velocity, which is 0, because Q was stationary before the collision, so plus 0. That's equal to the total momentum after the collision. Well, P had a momentum of 250, which is the mass multiplied by its new velocity, which is 1.15. And Q had a momentum of its mass, m, which is what we're trying to work out, multiplied by its velocity, which was 1.57. Rearrange, you're going to get m is equal to 1 over 1.57. Then 250 times by 2.1 minus 250 times by 1.15. I just did all of this in one step to save time in the video, but you could do it step by step. And if you do that, apparently what you would get for the mass is 151.3 kilograms. State one assumption you made in your calculation, or for any sort of momentum question that uses the conservation of momentum. The assumption is that the collision was in a closed system. Another way to say that is there are no external forces acting on any of the objects involved, or any of the cars involved in this scenario. So the collision lasted a total time of 1.35. Calculate the average horizontal force. Well, average force, which is the definition of force, is equal to the rate of change of momentum. So change of momentum over time. It wants the force on Q, so you need to know what is the change in momentum of Q. Well, after the collision, the momentum was 151.3, which is the mass, multiplied by the velocity, which was 1.57, minus the momentum before the collision, which was just 0 because it was stationary. So that was the change in momentum of Q. Over the time is 1.35. And if you do this in your calculator, you should get 1.76 times 10 to the 2 times 10 to the 2 newtons, which is 176 newtons. Good, let's continue. Explain why P decelerates during the collision. Your answer should make reference to Newton's laws of motion. Well, what we know is P collides with Q. When it collides, P exerts a force on Q during the collision. We know from Newton's third law, because P exerts a force on Q, Q must exert a force on P. Same magnitude, opposite direction. And now there's a force acting on P in the opposite direction to its velocity, so it's going to obviously decelerate. So let's try put this into words. So we're going to say, during the collision, P exerts a force on Q. So due to Newton's third law, Q also exerts a force on P in the opposite direction. Now P experiences a resultant force in the opposite direction with its motion. So from Newton's second law, which is F equals m times a, P will decelerate. A golfer hits a golf ball into the air at a speed of 52 meters per second at an angle of 41 degrees to the horizontal as shown. The ball landed on the ground near a hole. The ground was 11 meters higher than the starting point of the ball. Show that the vertical component of the ball's initial velocity was about 30 meters per second. Well, we're going to have to resolve the horizontal and vertical component of this 52 meters per second velocity. And we know that for any right angle triangle, where you know the hypotenuse And the angle, the side opposite the angle is hypotenuse, sine theta, and the side adjacent is hypotenuse, cosine theta. So it's going to be 52 sine 41, which when you put in your calculator, you get 34.1 meters per second. Show that the time taken by the ball to reach the ground was about 7 seconds. So to do this, I'm going to solve a vertical suivat. So SUVAT. The reason I'm doing that, I want to know the time it took for the ball to go up until it reached the ground, because it says the ball landed on the ground, which is 11 meters higher than the starting point of the ball. So this is the motion. So I'm working out the time it took for this motion to complete. So let's do that. The displacement is, well, it started on the ground and then it went up 11 meters by the time it landed. So it's plus 11. Displacement is 11. Initial velocity was calculated as 34.1 on the previous question. Acceleration is always minus 9.81 vertically because, you know, weight acts down. So the acceleration also acts down. And the time is what we're trying to work out. This is the letter left, so we're going to have to use the equation corresponding to this letter, which is S is equal to UT plus half AT squared. Let's plug in some values. 11 is equal to 34.1 T minus 9.81 over 2 T squared. This is clearly a quadratic. I guess let me put it in a quadratic form so it's easier to notice. 9.81 over 2 T squared plus 34.1 T minus 11 is equal to 0. We could solve this quadratic. You can use your calculator to solve it. That's what I'm going to do because it's the quickest way. Or you could use the quadratic formula, or you could complete the square. Or if you're some sort of genius, you could factorize, but let's use the calculator. I don't have a calculator, I lied, so I'm just going to use online. So I'm going to so what is our A, B, and C? So our A term, our T squared term is minus 9.81 over 2, minus 9.81 over 2. Well, I can't even divide by 2, can I? So 9.81 divided by 2 is 4.905. So minus 4.905. I should know this by heart. I don't know why I don't. 34.1 is your second term, and your third term was 11. So solve. Sorry, your second term was minus 11. Solve. So you get T is 0.34 and T is 0.61. So T is equal to 0.34 seconds and T is equal to 6. My memory. 6.61 seconds. We know that, like, if I were to draw the motion again, it went like this. And we're working out the time it took for it to have a displacement of, was that 11 meters. Well, the reason we have 2 times is because twice on the motion, it reached a displacement of 11 meters. The first time it reached this displacement was somewhere near the start, which we worked out to be 0.34 seconds. And the second time it reached this displacement was 6.61 seconds. So obviously we care about the second, we care about this time. So we're going to say, also it's a show that question, so it makes it obvious. We're going to say T is equal to 6.61 seconds, which is around 7 seconds. The hole is a horizontal distance of 250 meters from the starting point of the ball as shown. Deduce whether the ball landed within 5 meters of the hole. You should ignore the effects of air resistance. Okay, so to know if it landed within 5 meters of the hole, you need to know what is the horizontal displacement. So we know for a horizontal suivat, it's just S equals UT because there is no acceleration horizontally. So this is just 0. And you want to know what S is. So S is equal to the initial velocity, which is 52 cosine 41. That's the horizontal component of this initial velocity, right? This horizontal component, which we have to use because we're doing a horizontal smooth out, multiplied by the time, which was the time in the previous question, 6.61. If you do that, you should get, here they got 6.62. I think that's because they didn't round, we rounded. So yeah, you get 360 meters. So the answer is no, it did not land within 5 meters of the hole. A falling sphere viscometer is a device used to determine the viscosity of a liquid. A sphere falls through a cylinder containing liquid and the terminal velocity of the sphere is measured. Say why the temperature of the liquid should not increase during the experiment. So we know that as the temperature increases, the viscosity decreases. This will impact the terminal velocity, right? Because obviously we know from Stokes' law's equation that velocity depends on the viscosity. A scientist measured the terminal velocity of an aluminium sphere as it fell through the glycerol, show that the weight of the sphere is about 4.8. Okay, we know that weight is equal to mass. We want the weight of the sphere, so it's equal to the mass of the sphere multiplied by g. So we need the mass of the sphere. What is that? Well, we know that mass is equal to, so mass of the sphere is equal to, because look, it's given us density and it's given us diameter, which is usually used to work out the area or the volume. So mass of the sphere is equal to the density of the sphere, which is the density of aluminium, because the sphere is made of aluminium, multiplied by the volume. So multiplied by the volume of the sphere. So let's do that. So the density is 2.7. 2.7 times 10 to the 3. The volume, it's a sphere, right? So it's going to be 4/3 times by pi times by the radius cube. It's not giving us the radius, it's giving us the diameter. So you're going to do 7/2 multiplied by 10 to the minus 3 cubit. And that gives you the mass. And then of course we have to, let's say this gives us the answer A. Then we're going to have to do weight of the sphere is equal to the mass, which is A multiplied by 9.81. And if you did that correctly, you would have got 4.76 times 10 to the minus 3. Don't forget the unit, which is newtons. The terminal velocity of the sphere was 4.05 times 10 to the minus 2. Deduce whether Stokes' law deduce whether Stokes' law applied to the falling sphere. Well, if Stokes' law applied, then this equation applied, which is F is equal to 6 pi velocity eta r. So what we can do is work out this drag force. We'll start by working out this drag force using the values given. So F is equal to 6 pi times by 4.05 times by 10 to the minus 2 times by the viscosity, which is 9.5 times 10 to the minus 1 multiplied by the radius, which was 7/2, right, half the diameter, times 10 to the minus 3. So this is your viscous drag. Let's say we worked it out and we got some value A. And now what we're going to do is consider, okay, this is the friction you would expect. This is the drag force you would expect if Stokes' law was valid and it applied. Now let's work out the actual frictional force in real life. And to do that, let's consider the force diagram. The force is acting on the sphere because it's falling. Well, you have weight downwards, and upwards, you have upthrust and this frictional force F. So we're going to say weight is equal to friction plus upthrust. We worked out the weight on the previous question. So let's rearrange and work out what this force F is and compare it with our first answer. So F is equal to weight minus upthrust. And the weight was 4.76 times 10 to the minus 3 minus the upthrust. We know upthrust, so we're going to say upthrust is the weight of the fluid displaced. So the mass of the fluid times by g, which is the density of the fluid multiplied by the volume of the object, because that's the volume of the fluid displaced from Archimedes' principle multiplied by g. So this is the upthrust. So let's do that. So minus the density given as 1.26 times 10 to the 3 multiplied by the volume, which is just 4 over 3 pi r cubed multiplied by 9.81. Let's say you did this in your calculator correctly, then you would have got the following values. So for friction, you would have got 6 pi blah, blah, 2.54 times 10 to the minus 3. So you'd have got 2.54 times 10 to the minus 3 newtons. And then for this one, you would have got, so weight minus upthrust, also 2.54 times 10 to the minus 3. The reason they're given the answers in 3 significant figures, which is what you have to do, is because notice everything in the question was also given to 3 significant figures, right? So clearly they match, so therefore it can be applied. Therefore can be applied. Stokes' law is valid. State one condition that must be met. Well, we know the conditions for Stokes' law. It has to be a spherical object and it has to be laminar flow. So small speeds are required for laminar flow. So yeah, laminar flow and spherical object. Those are your 2 conditions. A scientist used a viscometer to measure the viscosity of blood. The viscosity of blood is typically in the range of 3 times 10 to the minus 3 to 4 times 10 to the minus 3. Explain why the scientist should use an aluminium sphere with a much smaller diameter than the sphere used with glycerol. Do not include calculations in your answer. And it's giving me the viscosity of glycerol once again. So clearly what we notice straight away is the viscosity of blood is smaller than the viscosity of glycerol. Because it's smaller, the sphere will travel a lot faster through blood because there's less viscosity, so there's less frictional forces opposing it. So it will travel a lot faster through blood as the frictional, or let's say the viscous drag acting on the sphere will be slower. It will also take longer to reach terminal velocity. We know this is a problem. And we also know Stokes's law requires, and this is we're going to use a condition we just spoke about for IAI. Stokes's law requires laminar flow, i.e. low speeds. So Stokes's law requires low speeds. This, we might not get this in blood because it's traveling too fast. Furthermore, I'm going to say that percentage uncertainty calculated for the terminal velocity will be much larger. Why? Because you're traveling faster, and you know uncertainty is percentage uncertainty is uncertainty of the measurement. Your measurement's going to be much smaller because the time, you know, it takes less time because it's traveling faster. So you're going to have a larger percentage uncertainty. So now let's talk about why should we use a smaller diameter. So we're going to say a sphere with a smaller diameter will travel slower through the fluid. The forces balance out quicker, so the opposite of before. So therefore, you will have a sufficiently low speed which will reduce the percentage uncertainty in the calculated terminal. It will also ensure low speeds for Stokes's law to be applied, or to be valid, sorry. Good. Okay, so that's the end of the paper. Have a lovely evening.